the past one before performing clustering. If it is same, then we have attained an effective clustering, an approximately effective one. If not, you need to keep repeating this. A good way to terminate is, to have a upper bound of number of iterations you want to run, and keep checking till your mean doesn't change for each of the centroids of the clusters. So the implementation of C code. The C code is divided into 3 libraries. The first one is the vector space creation, which has discussed before. This has 2 implementations, a serial one and a parallel one. And the next library is document clustering, which has both serial and parallel. Once the vector clustering, the vector space creation is done, these are sequential process. You can do document clustering only once vector space creation is done. And once that is done, document clustering uses the similarity score library to find cosine similarity in order to find the distance between the document being processed and the centroid of that particular cluster. Okay, I'm going to demonstrate this implementation. It's a C code implementation. I'm going to demonstrate it on a terminal on the CPU, both the serial and the parallel version. Let me switch back to the code. Okay, here you see the main.c. The main.c contains a header file, words.h, which contains the collection of words, the pool of words. And the main.c is the one which I referred to, the vector space creation, while the document clustering.c takes care of clustering, which has the k-means algorithm, and the similarity.c is used to find the cosine similarity. It's basically the dot product of the vector space. I'm still okay. Now let me just compile this code and let me check the parameters that I'm using for this particular clustering. So I've set the number of documents as 1024. The number of clusters to be created, let me keep it as 16. The maximum number of words per document is 30, and the total pool contains 200 words. Let me compile it and let me run. Okay, it generated the data. It is taking some time. Okay, it's taking some while. So it took 14.58 seconds, and the number of unique words that were found is 200. So all the words from the pool were used to create the document, and the number of iterations taken is 23. So what I could do is I could run this again to show you the final output of the clustered documents. Let me enable the flag that is in the document clustering. And to run it quickly, let me just reduce the number of documents. Okay, from 1024 to 512 documents. And if I run this, it should show me the final clustered documents into 16 clusters. So here you see, this is the cluster number 16, cluster number 15, 14, 13. Okay, we run out of number of the buffer lines. Yes, Okay, now let us check the parallel implementation of the k-means text clustering. So in the parallel implementation, the changes made is in the initial vector space creation. This happens in parallel. So this structure process document, the first part, the pragma, which is in quotes, that's the parallel section to find the unique words. So the strategy here is, if there are n threads, then compute unique words individually for those n threads by having n lists, and then once you're out of this parallel region, you merge all these n lists into one list having unique words. The next parallel section that you can see, annotated using hash pragma parallel, is a loop which is equivalent to number of documents, and this loop would run totally in parallel as there is no data dependency, because you're creating a vector space for every individual document with the help of the unique word list. So this happens in parallel and there is no synchronization required. The other parallelization that has been done is in document clustering. Here you end up creating here the clustering is done for all the documents using n threads if there are n cores. What happens here is, like, you have something similar to the initial a vector space creation, finding unique words, where each thread creates its own unique list. Here what happens is, like, if there are like 1024 documents, they're divided into by n, 1024 by n chunks. Each thread processes 1024 by n, and then this is processed in and made an own bucket. That bucket contains the document list belonging to that particular centroid. So n threads create n buckets per cluster. So if you have k clusters, then you get n buckets per cluster, and total of n into k buckets for total number of the clusters you're going to create. After this parallel region is over, you merge all those buckets with respect to a particular cluster group, so that you get one cluster having all the actual documents which are similar to it as compared to the sequential version. So let's just give it a run. Let's check out the initial parameters. Let's reduce the number of documents to 1024, and the number of clusters, let us increase it to 16. Let me compile it. And the previous one, the sequential version, took around 19 seconds. This one, let's check out. Yeah, it takes just 2.32 seconds. Like, it should be almost like 4 times. The previous one, I suppose it took 9 seconds actually, not 19. So yeah, it should be close to 4x speed up, because this has 4 cores. This has been run on Tellera, which has 36 cores. I've just scaled it up to the power of 2, that is 32 cores. And this is what the results look like. So I have varied here the description or definition of K, P, and W is: K is number of clusters, P is the pool of words that you are using to create the documents, W is the size of the document, the maximum number of words that an individual document contains, but this is the maximum upper limit. So you could see that the fastest one is with the 4 cores, and the one which takes maximum time is a cluster with 4, and the number of words is 200. You could check out the timing on the left side in the table. And this is how the Tile GX36 performs. You could see that single core performance of Tile is poor compared to the Intel i7 because Intel i7 cores run at the higher clock speed and they're pretty powerful. Whereas the Tile GX, those are a little simpler cores and run at 1 GHz, but when you scale it up to 32 cores, you get tremendous speed up and it outnumbers the Intel i7. So, at a lower power, it is performing better. So this is the readings for the parallel and the graph was plotted previously. Okay, what is to be taken from this implementation? As we know, the web is exploding with data, especially if you see the social network, and in future every application is going to have a component which would require text clustering. Text clustering is a challenging process because of the huge size of data that you have to manage and process. Parallel implementation provides a good performance boost, as observed in the parallel k-means text clustering. For future clustering needs, it is necessary to consider low-power implementations and explore them on such platforms. And eventually, the most important part is exploring and improving the clustering algorithm itself. That would give an acceptable grouping of the objects in a set. Yeah, thank you.